So today we're going to start thinking more about fundamental ideas and architectures for reinforcement learning and planning, and how to combine these ideas together. So really it's, there's a lot of conceptual ideas. There'll be much less math in the last couple of lectures, and more just about understanding what it means to do planning, what it means to do learning, what it means to combine these things together. And so rough outline for today, as we'll start off, I'll introduce the area, as usual, a little bit. But then we're going to start to talk about one of the fundamental areas that we haven't explored so far, which is called model-based reinforcement learning. Up to now, pretty much the entire course is focused on model-free reinforcement learning, i.e. where we don't explicitly try to understand and construct a model of the world's dynamics. And in this lecture, we're going to start breaking that apart. We're going to start to talk about, what does it mean to build a model of the environment, and how can we then use that model to plan and perform more effectively in that environment using that model. In the third section, we're going to start to talk about how to pull these ideas together. So we've seen up until now model-free based approaches, and then today we're going to look at model-based approaches, but can we get the best of both worlds? Can we combine these together into a single integrated architecture? And so we're going to talk about Dyna and other ideas that combine both model-free and model-based methods together. And then finally, we're going to talk about a family of methods that actually are all about planning, simulation-based search, but the main idea there is that we plan by applying reinforcement learning to simulated experience. So this final section is all about architectures where you have some agent, it imagines what's going to happen into the future, and it learns from that imagined experience how to perform better, and we'll see that that actually gives us surprisingly effective algorithms for planning within the reinforcement learning context. Okay, that's the sort of map of today. So it's playing with these ideas of learning and planning, understanding what they are, putting them together in interesting ways. Okay, so just to start with an introduction then. So in the last lecture then, we started off by, we were looking at these policy-based methods. We learned a policy directly from experience. We looked at policy gradient methods, policy search methods, where we had some agent, ran its trajectory of experience, the robot's wandering through its environment, and at each step it looks at the experience, it looks at the reward it's receiving, and it says, how can I actually adjust my policy so as to do better? In the previous lectures, we looked at learning the value function directly from experience. Again, you see some trajectory of experience, and you use that trajectory to update the value function, and then indirectly use that value function to behave better within the world. So in this lecture, we're going to try something different, which is instead of learning the policy or the value function directly from experience, we're going to learn a model directly from experience. And what we mean by a model is something where the agent starts to understand its environment, starts to understand the dynamics of the environment, how one state transitions to another state, and to understand the reward that environment will bestow for any given action in any given state. So we're going to try and learn that model directly from experience. So we have now our robot wandering around. If it takes a step, it's going to say, okay, well now I know that if I was in this state and I took the action of stepping forward, then I'll end up something like here, and I'll get a reward of whatever reward I observed. We'll use that model now to plan. And what do we mean by planning? Well, just think of something like tree search. Imagine you've got something like a chess playing agent, and it's doing a search tree, and it's trying to look ahead. So what we mean by planning is something like look ahead. We're trying to figure out, by using our model to imagine what might happen going into the future, we're going to use this process of look ahead to construct a value function or a policy. So all of the ideas from the first two lectures can still be applied here. Ultimately, we're still going to be building value functions and policies. We're going to be building them by using this model to perform look ahead, to understand what the environment might do by invoking our model instead of interacting with the real world. And so what we're going to try and do is then integrate these ideas of learning and planning into a single architecture. Okay, I guess the power's not on for some reason, which is why this is blanking. Let's try that. Yeah, good. So I just need to wait for that to come back to life. So what we're going to start with is, we'll start off by understanding what it means to build a model. A model, again, is something which can be broken down into two pieces. A model is something which tells us all about the transitions, about how one state transitions into another state, but a model also tells us about the reward component of what's happening. So there's always these two parts to a model. So what we mean by a model is perhaps one of the most overloaded terms in machine learning, or perhaps even science, where a model can mean many things to many people. for us in this lecture, it's going to mean something quite specific. It's going to mean something which describes, for any given environment, it's the agent's understanding of that environment, the agent's model of that environment, the agent's understanding of how states transition to other states, and how states lead to rewards. And when we have those things, we should be able to actually plan with them to do look ahead and figure out how to do better in that environment. I'm just waiting for my laptop to come back to life. It doesn't seem to want to do. Okay. Now we need to wait for the projector to come back to life. And then we need to wait for you guys to come back to life, and we'll all be good. So, let me just try this. Okay, so let's start to come back to our taxonomy that we saw in the very first lecture. Throw your minds way back into the past. We broke down reinforcement learning into two types. We broke it down into model-free reinforcement learning and model-based reinforcement learning. So what do we mean by those things? By model-free reinforcement learning, well, we mean there's no model. What do we mean by that? Well, we mean that the agent doesn't make any effort to explicitly represent the transition dynamics or the reward function that the environment is operating under. And instead, we learn a value function and or a policy directly from experience. So you have some agent, it's wandering through, it applies its favorite algorithm, Monte Carlo learning, TD learning, policy gradients, whatever it is, it applies that directly to this stream of experience and comes up with some way to estimate how much reward it can get, or how some way to directly come up with a mapping to which actions to pick in the last lecture. That's model-free reinforcement learning. But today, we're considering model-based reinforcement learning. So that means specifically anything where the agent explicitly represents and learns a model from experience. So now it sees its experience, and it uses that experience to construct an estimate of these transition dynamics and rewards. And it uses that model then to plan a value function and or policy from the model. So what we mean by planning is basically using a model to look ahead, to think, to compute, to figure out what the right value function or the right actions are to select in this environment. We'll see more examples of that as we go through. So if we go back to our original picture that we had for model-free reinforcement learning, it looks something like this. This is the reinforcement learning cycle we had in the first lecture. We've got our agent brain there, thinking about what to do. There's some environment it's in, whether it's the factory floor it's on, or the chessboard, or whatever the situation we've thrown this thing down in. And it gets to take some actions. At every step T, it gets to take an action. And then from the environment, it sees some reward and some state. That was our fundamental cycle of reinforcement learning. So what do we do in model-based reinforcement learning? Well, what we start to do is we replace the real world with the agent's model of the world. So this cartoon version of the world is supposed to represent the fact that we've basically taken away the real interactions that the agent's having, and we've replaced those real interactions with simulated interactions with a model of the environment. So here now we've got this agent, it's doing exactly the same things, it's taking actions, but now with respect to its internal model, its imagined world. It says, well, hang on, I can think about this. I've got this model of the world. I can imagine what would happen if I stepped forward in this world. How much reward would I get according to my model? What state would I end up in according to my model? And then I could pick another action. I can say, well, if I followed up from there and I took a second action in this world, how much reward would I get? And what state would I end up in? So I can do look ahead, I can roll these things forward, I can build search trees, I can start to think about it, I can start to sample random transitions and figure out what the value function could be, all internally without actually taking any step in the real world. So this gives us the ability to think, to figure stuff out, to look ahead, to plan, and to basically start to understand the best actions to take and improve our policy, improve our value function without any further interactions with the environment. So that's what a model gives us. It gives us the ability to think, to look ahead. Okay, so let's talk about what model-based reinforcement learning is, just try to define it a little further. So model-based reinforcement learning, we can kind of define it by this cycle now that you can start anywhere on this. I think I would like to start somewhere here. that we have the agent's actual experience. This is it really interacting with the real world, not the cartoon world now. From the interactions with the real world, it's going to build up its model. It's going to learn how that environment acts, how the environment, what the environment does. Every time you take an action in the world, you take some action in the real world, and now you see that actually that led you somewhere. That took you opened a door and you saw some new room. You now change your model to understand what happens when you open the door. Once you've learned a little bit more about your model from your experience, you have a model, and you use that model to plan. This is like your look-ahead process. This is now the slide I just showed with the cartoon version of the world, where you start to have interactions with that model, and the interactions with the model generate a value or a policy, a value function or a policy. And that value function or a policy you then use to act in the real world. So the main idea now is we've interjected, instead of just looping around here, we've added in this model step, where we're using our experience to build a model, and we're using the model to plan and figure out what to do next. And now as a result of that planning, we can make better actions in the world. We can start to really squeeze more out of our model to really start to figure out to solve our model MDP, if you like. So you can think of this as learning an MDP model, and then here, plan is like solving that MDP, like doing our dynamic programming or figuring out the solution, figuring out the optimal value function or the optimal policy for the MDP that we believe we're in. And then each time you see more experience, you might update your estimate of what MDP you think you're in, so that now when you solve it again, you end up with better actions and do better and better in the real world. So that's model-based reinforcement learning. Really fundamental idea. So it's natural to ask, well, should I do this? What's the advantage or disadvantage of doing this? And I think, perhaps the clearest example would be to take a domain where learning a value function or a policy directly is hard. So imagine you're playing chess, for example. Now, there's a huge variety of different states that you can be in the game of chess. I think there's something like 10 to the 48 or something different states in the game of chess. And if you just move one piece by one square, it can completely change it from being a won position to a lost position. So it has a very sharp value function, which you just move from one of those 10 to 48 states to another one, and suddenly your value function or your policy completely change. That means it's a hard problem to learn a value function or a policy directly. However, the model is quite straightforward. The model is just like the rules of the game. That if I move the pawn forward 2 steps, then I will be in a new board position where that pawn has been moved. The model is relatively straightforward. And so if I can use that model to look ahead, I'm able to estimate the value function by planning, by tree search in the case of chess. And that's why tree search is powerful in games, because it gives you the ability to construct a more accurate value function when it might otherwise be hard to estimate that thing through our normal means directly from experience. So really that's perhaps the main advantage is that sometimes a model is a more compact representation than a value function, or not just more compact, a more useful representation of the information about the environment than you might access directly by a value function or a policy. So in addition, it's also possible to efficiently learn a model by supervised learning methods. Like one thing which is nice about model learning is like I was in this state, I took a step, and now I'm in another state. So now by supervised learning, I can say that the input is being in this state, the output is whatever state I ended up in. And it's like there's some teacher saying, look, whenever you start in that state, you ended up in this state. And now you've got a teacher that tells you the right thing, we've got a supervision signal, we can apply supervised learning to figure out the dynamics and the rewards of our model. We can start to learn our MDP by supervised learning. We don't need to wait all the way to the end of our trajectory to figure out where we were after 1 step or 2 steps. And a lot of people talk about model uncertainty as well as one advantage of being model-based. Right? If you want to understand, so sometimes the exploration problem in reinforcement learning is you want to take actions that help you understand the world better. You don't just want to take actions that get the maximum reward from your current view of the world. You also want to figure out if maybe your understanding of the world was wrong. And the model gives you a very useful way to reason about what you know and what you don't know in the world. The model basically tells you all the things you know, and so now you can choose, if you understand your model uncertainty, you can take actions to take you to states where you don't understand the dynamics of your environment very well, and choose to go there. main disadvantages, well, now we've introduced another moving part to our reinforcement learning algorithm. Like first we're learning a model, and then we're using that model to make a value function. So before, if we were just learning a value function, the only place that our errors could crop in were, we could get errors in if we were using value function approximation, then that value function approximator could introduce bias and error into our estimates of the values. Now we've got two places errors can creep in. Like our model might be approximate, and then we're using that approximate model to learn a value function, which might also be approximate. And so there's like two places the errors can creep in, and these things might compound. We're only going to be as good as our model, as we'll see later. If you learn an incorrect model and then plan with it, you will get an incorrect answer. And so what we'll try to do actually later on in this lecture is we'll try to combine the advantages of model-free and model-based reinforcement learning into a single architecture. So what is a model? So I've kind of said this informally, well let's say the same thing formally now. So one choice for a model is that it's a representation of an MDP. That the world that we're in is some kind of MDP. We might not know exactly what the underlying states and transitions and so forth are of this MDP, but a model means to estimate these things. A model means our view, the agent's view of what the MDP is that it's living in. And so let's say that there's some representation of an MDP with some state space, action space, transition probabilities, and reward function. That was our definition of MDP from earlier in the course. And we're going to parameterize this thing. So think of this as now just like, maybe it's a neural network that we're trying to learn with some parameters. And we'll use these parameters eta to represent our model. And we're going to assume that our state space and the action space are known. You can have more complicated versions of model-based reinforcement learning where you also try to learn the state space or the action space. We'll do the simpler case. And so the model now is basically the parts that we don't know that we're trying to estimate. The transition probabilities, like if I'm in some state, what's the probability that I'll move to some next state, and a reward function. And these things are going to just be parameterized by by these parameters eta. And so we've got two things. This is just our usual definition of MDP. We've got something which says, if I was in some state ST and I took some action AT, what's the probability that I'll transition to this next state? And we learn that thing. That's what it means to learn a model. We learn the probabilities that we transition from one state to a next state, the dynamics of the MDP, where the wind will take you next, or where your helicopter will move to if you apply particular controls, and where your robot will move to if you adjust the torques in its motors, and all these things. But we also learn the rewards. And so the reward function is basically just saying, what will the reward be, the expected reward at the next time step, if I'm in some state and take some action. And so both of these are one-step models. You can do longer timescales as well. Here we're talking about one-step models. We're looking at what will happen at time step t plus 1 if I start in time step t. And so you only need one step of experience to learn this thing. You get, for example, you can learn this thing. You started in state st, you saw state st plus 1, you can already learn. You don't need to look at successive state transitions after that. Okay. And for this particular definition, we typically assume these things are just independent. We can learn them separately. It's easy to change that. Yeah, question?
I think that I don't quite understand the chess example and what you gained from using the model-based view of things. So when you're doing model-based learning, the dynamics are still, they're sort of fixed. There's no like probability distribution. It's like only one. If you make an action, then you deterministically transition from state to state. So you still have to learn the reward function. And is that not just the same thing as doing it like in a purely value-based way?
No. So good question. So the question is, isn't it the same to learn a reward function as to learn a value function? And the answer is no. Like in chess, what would it mean to learn the reward function? Well, the reward function in chess might be something like 0 for losing a game and 1 for winning a game. And now all you need to learn is that if you're in a checkmate position, that you lose, and if you've checkmated your opponent, then you win, and if it's a stalemate, then it's a draw, 0.5 reward. You don't need to, whereas if you're learning a value function, you need to learn about all the states where it's not a terminal position. You also need to learn, if I'm in some complicated position with all these pieces distributed around the board, and and there's still a lot to play for in that position. The reward learning problem is easy because the reward will always be 0 in that situation. The reward function is just 0, 0, 0, 0, 0 until the end of the game, and you either win or lose. So that's an easy learning problem. You're just learning that the reward is 0 unless you're in a checkmate position. So that learning problem is much easier. You're just learning to classify positions as checkmate or not checkmate. And that's just about learning, does the king have any moves left? Whereas actually learning to understand, am I likely to win from this position? Like, I'm in some early middle game position or something. What's the probability that white will win from this position? That's a complicated learning problem. Now you need to figure out, well, actually from this position, maybe there's a 72% chance that white will win from here. It's a complicated thing. And so the main point I'm trying to make is that there are situations where it's really an argument that planning sometimes helps. Like, the being able to plan sometimes helps, because trying to learn the value function directly, there are at least some cases, like these very tactical games like chess or Go or whatever, where it's necessary to plan to figure out exactly what the situation you're in. That without doing this process of look ahead, it's very hard to say who's ahead or who's behind in the position.
Okay, and so like the being able to look ahead and plan is not like a valid move to make when you don't have anything
So planning necessarily means that you've got some way to roll forward your state to say what would happen if I was in some. So if we take chess as an example, what's the model in chess? It's basically the rules of the game. Okay, it's the thing which says I'm in this position. How do and I take an action. What position will I be in next? So it's just the rules of the game. That if I take this move, certain moves might remove pieces from the board, or they might just change where things are. And so we're just trying to understand the rules of the game then. And if you don't tell anyone what the rules of the game are, then that would be model-based reinforcement learning. You kind of have to figure the rules out and then use those rules to plan with. Or we could just consider the planning problem without the whole reinforcement learning problem, which would be someone tells us the rules, someone tells us the MDP, and now we need to plan with it to figure out what move to play. So those are both interesting problems, but the chess example is just to illustrate the case that there are some situations, there are some MDPs where it's very hard to do well in that MDP without planning. So there is a case for being model-based. Okay, so we're going to take this idea of trying to learn an MDP. We've got our transition dynamics and our reward dynamics. And in general, so chess here, it isn't maybe the best example for this, because chess is deterministic. Here we're trying to understand, well, what happens in stochastic situations where you've got a helicopter and the wind might blow it one way or the other. We want to learn that as well. And so the goal really is to estimate this model from experience. So we've got our model, our MDP, parameterized MDP, maybe our neural network representing what's going to happen next, or our linear function approximation, or whatever it is. And we just see our experience, our usual stream of experience, states, actions, rewards, until the end of the trajectory. And but now it should be relatively clear that we can actually just transform this one into a supervised learning problem. So specifically, I was in state S1, I took action A1, and I ended up seeing an immediate reward, that was the reward we got from that time step, call that R2, and the state that we ended up in, S2. So that's just after one immediate step. We see what reward we got, we see where we ended up, and that becomes an example that we can learn from. And then we've got another example, which is then I was in state S2, I took action A2, I ended up getting some immediate reward, and ended up in some new state. That's another example. We collect together all the examples that we see from all of our trajectories. That gives us our training set. We can use that training set to basically do regression to learn the rewards. So we're trying to now split this into two parts. We're going to split it into the reward part and the state transition part. You don't have to split it, but it can be useful. One reason it's useful is that these are kind of different types of supervised learning problems. So to learn the reward function, we're just trying to learn what's the how much reward will I get in expectation from taking some state S and some action A. If in S I take action A, how much reward do I expect to get? That's a regression problem. We're giving an input to our regression problem of state and action pair. We're trying to estimate how much reward we'll get. We're just going to use all of these as examples to train this regression problem up. But we've also got a density estimation problem. We're trying to learn something stochastic, which is if I'm in this state action pair S comma A, if it's a stochastic environment, I might say, well, I want to learn the whole distribution over what next state I'll be in. Like maybe there's a 30% probability the wind will blow me left, 70% probability the wind will blow me right, and I want to estimate this whole density. And so we can transform the model learning problem into two types of supervised learning, and then pick appropriate loss functions for these things. So if you're doing regression, you might choose to optimize for mean squared error. If you're doing density estimation, you might choose to optimize for KL divergence, like make your distribution as close as possible to the empirical samples you store. And I'm not really going to go into the details of how to do this, except for one simple case. And really the idea is just to find the parameters that minimize our empirical loss. So we see all of these examples, and we want our loss to be as small as possible across these examples that we've seen so far. So that's how to do model learning in a nutshell. And you can kind of apply, so everything that you've ever seen in supervised learning can be applied here. And really that's all I'm going to say about it, except for this question.
In this situation we're considering here, do we know our state space, or are we actually able to, say, make our own features?
So for the purpose of these slides, we're assuming that we know the state space and the action space. In general, yes, of course, we want to learn our own features, and that's typically a very good idea, and it may well not be the case that the raw inputs that we're given are useful for learning the transition dynamics, and you might well want to figure out a better representation of the state space that helps you understand how the MDP is rolled forward. So you can also choose to learn the state space or indeed the action space, but that's a more complicated version. So let's just make this concrete by thinking about examples. So I will talk about the simplest possible case in the coming slides, which is the table lookup model, where basically for every state action pair we estimate the reward and the next state separately. In general, of course, this doesn't scale, and it's usually a bad idea, so you can pick your favorite approach. You could make a linear model, where you basically say, you know, what's the expected next state if I have some features describing my state in action, what will my expected next features be? So we can basically apply a linear model to our feature vector and say, I start off in some features, you know, I'm this far from this landmark, this far from this landmark, and now I'm going to make a model that says, you know, if I go forward, then I'll be a little bit further away from this landmark and a little bit closer to that landmark. You know, a model that sort of in expectation tells us what will happen by making, say, a linear map from features to features. We could have a Gaussian model to, rather than just making an expectation model, we could, you know, model the whole distribution of next states using, say, a Gaussian. You can take that further and have a Gaussian process, a non-parametric model. You can have a deep belief network to, you know, pick your favorite supervised learning method and your favorite representation, and you will be able to apply it here. ... means a lot of possible things. Okay, let's consider the simplest case, the table lookup model. So what's a model now? A model is sort of an explicit representation of the MDP. And so if we want to basically understand from this state, if I consider some specific state I was in, and I want to know, well, I'm going to keep a separate representation for this state of where I will go next, if I start in this state and take a particular action, all I need to do is count. I just count how many times from here I count, and maybe I ended up over here 10 times, and I ended up over here 5 times, and so now I just count those things and use the empirical counts to give me a probability distribution over where I'll go to next. So this is just saying the same thing in maths, saying that our transition dynamics are going to be the average of this indicator function, which tells us every time I ended up in this particular S prime, in this particular state S prime. We're just counting the times I ended up in that particular state. And the reward function is basically just taking an average. All the times I started in this particular state in action, let's take the average reward, the mean reward of all of the rewards that I got from that point onwards. So this is just the intuitive thing. You know, don't even need to look at these equations if they're confusing. It's just using indicator functions to say, let's do the obvious thing, which is to count the transitions and assign my probabilities proportional to those counts of where I ended up next, and to take the mean of the rewards that I've seen so far and to use that as the reward function. So, is that clear, first of all? Good. But there is an alternative way to set up the same model, and the alternative is to basically just remember things. So you can just record the experience that you've seen so far. So you can just record that when I was in state ST and took action AT, I observed reward T plus R root T plus 1, and I observed that I ended up in state ST plus 1. And now, if you want to actually sample from this model, all you need to do is take the set of tuples that are consistent with the state and action that you want to know about and sample it uniformly at random from those. And then you sample, well, one of these rewards was that, and one of these next states was that, and you can just sample from those tuples. It's equivalent. Here we're going to talk, so it's basically a parametric and non-parametric approaches. So those are examples of the two families of functional approximation for model learning. But they basically give you the same information. Okay, let's make this concrete. So we've had this example once before, but I'm going to take it just one step further in this class now. So we had this really simple A-B example when we were talking about understanding temporal difference learning. So we're going to use it for a different purpose here, which is we're going to do model learning. So just to remind you of this problem, we've basically got two states with no discounting, and we just see these episodes of experience from state A and state B. So this means on the first episode, I started in state A, got reward 0, then went to state B, got reward of 0, and then the episode terminated. Second episode, I started in state B, saw a reward of 1. Next episode, started in B, reward 1, until finally started in B, got reward 0. So we can take this experience, and as we did before, we can build a model from this experience. This is what we saw in the TD, that TD was kind of doing implicitly. Now we're making that explicit. We're explicitly building this model. So we're going to build the model, the table lookup model, that corresponds to these counts and these rewards that we've seen. And so all we need to do is to count and say, well, every time I was in A, I transitioned to B. So if I count those things, I can make this transition here to say 100% of the time I transition from A to B. And I can count that from B, on 6 out of 8 of my occasions, I transitioned to the terminal state with a reward of 1. And on 2 out of 8 occasions, I transitioned to the terminal state with a reward of 0. That gives me these two arcs here. So it's just counting. That's all that's required to make a table lookup model. So now we've got a table lookup model. Let's use it. Let's start to understand how to use this thing. So the next step is, and this is the important step, is to plan with the model. So far we've just talked about learning a model. What does it mean to plan with a model? So now we've got our MDP that we've learned. We've estimated our MDP, for example, the one on the previous slide. And so now planning basically means kind of solving that MDP. It means using that model that we've got to try and find the best thing to do. And so we're going to solve that MDP to find the optimal value function and the optimal policy, and hence pick the best action. And so you can use your favorite planning algorithm to do that. And we've seen a bunch already. We've seen in earlier lectures dynamic programming methods like value iteration and policy iteration. So these methods, when we talked about them before, we thought, okay, well, you can't use these to do reinforcement learning because you have to be told what the MDP was to apply them. But in this lecture, we're saying, well, actually, you can do reinforcement learning with those. All you need to do is learn your model, first learn your model, and now you have the model in your hands, so you can use that model to apply dynamic programming. Or you could use that model to do something like tree search, or a variety of other planning methods we'll start to talk about later. So again, let's make that concrete. And the method I'm going to talk most about in this lecture is what we call sample-based planning, which in some sense is the simplest possible way to plan, but it also turns out to be perhaps the most powerful way to plan. And certainly the empirical results support that, at least in complicated domains. And the idea is to only use the model to generate samples. So unlike dynamic programming, where you actually look at the probabilities of transitions and kind of integrate over those probabilities, we're just going to use the model to generate samples. We're going to treat our model as if it's the real environment, and we're just going to interact with that environment and see samples of where I end up. So instead of knowing that 75% of the time the wind will blow me right and 25% of the time the wind will blow me left, I'm just going to randomly sample something from the environment. I'm going to be like, oh, look, I got blown right on this occasion, and I'm going to learn from that sample, just like we do when we interact with the real world. So we sample a next state. If we're in some state S, A, I'm going to sample the next state, and I'm going to sample the reward from the model. And then I'm just going to apply our familiar model-free reinforcement learning to those samples. We know how to learn from sample trajectories. We know how to learn from samples where I've just randomly seen what happens if I interact with my environment, and the wind blows me around, and I take this whole sequence of actions, and I end up over here, and I get some sequence of rewards. That's the problem we've been studying all along, which is model-free reinforcement learning. So the main idea here of sample-based planning is to just use the model to generate samples and then to apply model-free reinforcement learning to these samples. Another way to